Yeah, we'll start today just looking at simple things you can do with a transformer. Because of course we have already looked at the sequence to sequence models, and we did a bit of hands-on, with sequence models, with recurrent neural networks, LSTM and GRU. Then we talked about the transformer architecture, right? So now I think we have seen this problem where we want to do next word prediction using LSTM. Now, we want to do exactly the same next word prediction using a transformer. So you see the slight differences and improvements in the approach. Remember, a transformer is just as a recap, if you want to look at the transformer architecture again, let me see if we have that in this slide. Yeah, so this is the slide where you can see transformer architecture. Um, in the transformer architecture, it's all about the attention mechanism, right? You have the encoder and you have the decoder. And the encoder is made up of two layers, right? Per encoder. Of course, the encoders can be stacked, so you have multiple encoders stacked. Inside one encoder, you have the multi-head attention layer, then the addition and layer normalization. Then after that is followed by the feed-forward layer, right? And that feed-forward layer, of course, is essentially two fully connected layers that are stacked, but the output of the first layer is much, much more in number than the number of inputs into that first layer. So it's typically like two times, three times, four times, or even more. And then that intermediate layer goes back into another fully connected layer. The output will be the same number of, same as the number of inputs. So you kind of have an expansion and then it is compressed back. So that's the feed forward, and then you have the addition and normalization. So these two form a single encoder layer, and then you have any number of it, right? Depending on how complex the problem that you're trying to solve. You can have a deep neural network of 10, 20, 50, 100, 500, or even 1,000 layers. But we're going to start with just a very simple one, right? Where we'll actually use an encoder because we want to do prediction. Typically, you use encoder. Classification, like we said before, if you want to do classification kind of task, you use encoder. If you want to do generation, you use decoder. Interestingly, next word prediction is a classification problem. But if we want to do real generation, we should actually use a decoder, right? Because that's a generation problem. But let's just do next word prediction. Now you can chain next word prediction and you actually find out that you can essentially generate. But that's not a very efficient way of generating, mainly because if you use that approach to generate, then you cannot have very large vocabulary because the output that comes from the um, prediction of the next word is essentially um, a distribution that the number of outputs should match the number of words in the vocabulary we're trying to predict. But I think another way would the output, the number of outputs, short size, embeddings. So you could also use embeddings. Like basically make your output a prediction. So let me just kind of show that so that what I'm saying makes sense. So here you have a pipeline that you have to put in place. So you have to always start with the text um, pre-processing pipeline. So here we have, of course, the normal imports. Then we're going to take text from this data set. This data set is called the IMDb data set. It's actually a data set of movies with their titles and a lot of additional data on these movies, right? So, of course, we are using yeah, first of all, yeah, this should run on a GPU. That's one thing you need to confirm first. So you can check that by checking on the runtime type. It's already showing a T4, which is a GPU. You can also have, actually, this is a collab Pro, so I bought a few units. Because I bought a few units, I also have access to an A100 and L4. These are a bit more powerful than the T4. Right. Then the H100 is like the latest architecture. This one will burn more of your credits anyway. So you can actually buy some credits on Google Colab. Basically, you're subscribing to what they call Colab Pro, and you have access to a bit of other GPUs, right? So anyway, we still take the T4 GPU. So the imports are done. Now we load the IMDb dataset. By the way, GPU doesn't do the data loading, so it's still going to be a bit slow, right? It's still going to be a bit slow. Um, okay, so I think I got an error here. It says okay, so I need to go and check. I did this IMDb already. Um, let's see. So it's basically the same thing. Maybe something has changed because this was definitely working before. Let me try again. Maybe the imports didn't come through properly. I think something has changed because this notebook actually was running just a few minutes ago. Um, Let me see how I can fix that. Okay, so I have the same problem here. I think I need to install it. So let me just install just to be sure that I have the right um, uh, the, the right version of data sets. I don't know. So we install data sets and touch, right? Let's see if it still gives me the problem. Okay. Um, okay, so anyway, we'll just move on. I'll come back to address this. So typically when you do this, you're going to load a data set that contains training data and text, right? Training data and test data, right? Which is basically text corpus that you can use for training your models. Then, of course, the normal processing is you have to do tokenization first. And after you do tokenization, um, then you do um, here the markdown is just to help us look at the tokenized text, right? So you can look at the original training text, and you see the original training text is just a stream of text. Okay, and it's typically since we are getting from IMDb contains um, some kind of commentaries on different movies, right? So we're going to use this to train a model to be able to predict the next word that will come, what's the likely next word that will come from this corpus of data. So this is going to give us a kind of insight into how um, training you know, what comes out when you train. So, yeah. So that kind of gives us an idea of how you know, the text, this is what it looks like. So the first thing we'll do is to tokenize this text, right? So when you tokenize the text, yeah, we'll be able to, this is the tokenization part. So you can see that we have a loop that's calling this tokenize function. And because our tokenize function is a very simple tokenizer that just takes the text and splits it into words using word boundary. Basically, that's what this does. It splits it using spaces into different words, right? So that's the first step. Then the second step uh, after tokenization is put those words into a vocabulary. You always need vocabulary, right? You always need the vocabulary. Yeah, okay. So I've seen that this this failure here is due to a recent change in Hugging Face. Obviously, we are loading this from Hugging Face. So there's a recent change. We have to put a prefix, the namespace name. We have to put in the author or owner of the database. So let's see. There are some examples here. Stanford NLP. NLP. Let's see if that works. No. Okay, so that works. Okay, so yeah, so we'll load the data set. So this data set, we can print it again and you'll be able to see. But yeah, we'll have the tokenizer. We have a markdown. Um, this is just to allow us to properly show the text as markdown. So again, this is the same text, right? Um, so you can see this is a lot of text. And when you want to train language models, you actually need to bring a lot of text. This is just the first 10 reviews of this movie, just 10 sentences or 10 paragraphs rather. So imagine we are having about 2,000 of these. Okay, so now what this section does is that it is taking the text for each of the texts which we have gotten from here because the text contains both training and text, right? It has both training, which is dataset train text. That's the training text. Then there's also a test, you know, sub list that contains the text for testing if you want when you want to use and run your tests. So we get the training part, and here you can see that we are getting just the first 1,000. The number is actually quite longer, much longer than this. If we even just run it now, um, train text, if we take this train text, I actually truncated it here. So let me take the original data set and check the length. You see that it is much, much longer, right? So you could actually check the length of the original text and you see that there are 25,000 different paragraphs, 25,000. And this is actually small. These days, large language models are trained on much, much more data. But yeah, so we now take each of the text in this train text. We had trimmed it down to just the first 1,000 because we are doing a demo. When you are doing this, eventually it's going to take much longer, right? But because I need to get to the end of this demo, right? Okay, it's already telling me that I'm not using the GPU, which is okay because we've not got to the point of using GPU yet. Even though all of this could be moved to GPUs anyway. So what I now do is that I tokenize the text. So we now have tokens, which is a list of the texts that have been tokenized. We now put those tokenized texts into the counter. So the counter, basically tokens are now words because we use a simple tokenizer that just splits the paragraph into words. So inside this counter, we now put each of the words. So what a counter does is that it gives you a frequency distribution of the different words or whatever you put inside it. So things that are the same, right? They will be counted together. So yeah, so we have um yeah, so you can see that we have a vocabulary size of 20,000. So effectively, remember we have 1,000 paragraphs. The data corpus contains, we trimmed it down to 1,000. But those 1,000 paragraphs, each paragraph would have, a lot more words, could have 100 words, 200 words, right? So when you look at it, total number of words could be 1,000 times 200. But of course, a lot of words are repeated. So it will not be that much. Now, we decide that we want to restrain or restrict our vocabulary, which is the total collection of all the words. We want to restrict it to just 20,000. So if somehow, for some reason, we have more than 20,000 words, we trim off the rest of them. And that's what we do here. Most common, right? So most common, we take the most common, which is this is a function in the counter that will give us the most common of the entries in the counter. And this number that we are taking is vocabulary size -2. Now the question is, why is it -2? Because we want to give room in these 20,000 words that we want to allow in the vocabulary. We want to give two spare slots. We reserve two slots. One is for the pad and the second is for the unknown. And that's what you're seeing here, right? So pad means basically what you use to pad words. Remember when we said, when we're doing sequence models last time, you know that sequence models can have different lengths. So for you to be able to handle different lengths, what you do is that you find the maximum length and then you pad to the left, right? On the left-hand side, you pad every sequence so that they all become the same length. So you now have to deal with same length sequences. But there's also another approach with sequence models where you could say, okay, instead of padding them to be same length, we would use a different approach to just train on different variable length sequences. But for transformers, we don't want to worry about that because transformers have fixed size of inputs, right? It's not sequential like the other ones, the LSTMs and so and co. So for transformers, we will keep a fixed sequence length. We'll pad anyone that is not up to that sequence length, we pad it. Anyone that is more than that sequence length, we will truncate it. We'll chop it off at the end so that everything is the same length. So what happens is that uh, the character that we use for padding is a special character, this pad here, so that we know that, okay, this is just padding. And we give it an index of 0 in the vocabulary. Then this UNK is for any word that is not in the vocabulary, an unknown word, basically. So this helps when you have trained your model on a particular corpus of data, a particular vocabulary, and then you ask it to predict, and there are some words that are not in that vocabulary. So the best way to handle that is to mark those words as unknown, right? So unknown is given an index of 1 in the vocabulary. So this is the 2 that we reserve. That's why the actual number that we pull from the counter is the vocabulary size -2. So we've already taken the first 2 slots in the vocabulary, for one for pad and one for the unknown. Then from there, we now continue from the remaining words for the words in the most common, starting at point 2. Remember, we've already taken 0 and 1 for pad and unknown. So we continue from position 2 and we fill in this STOI. STOI is basically string to index. So essentially, this allows us to get the index number of a particular string. So you're going to get all the words in this counter. That's why you're enumerating the most common, which the most common was in the counter. You're enumerating it and you are using it to fill in. So at the end of the day, when you finish, the STOI is going to give you, it's going to be a 2000 sized array, right? It's going to be a 2000 size array because most common is actually the 2000 most common words, or 2000 minus 2, which is 1998, right? 1990. Oh, sorry, it's 20,000. So it's actually 19,998, right? So that will be but the total length of your SUI will still be 20,000. So we will now fill that with those indexes. And then the I2S is the reverse. So we're now going to create a reverse lookup table that has the indexes as a key. That's the indices, the position or location or in the vocabulary, while the string, the actual word, is the value. So the benefit of having these two reverse lookup, the stoy and the itos, is if I want to check the index of a word, right? I use stoy. I put in the word and I get the index. If I want to get a word at a particular index, I use the itos. All right. I check the index and then I get the word out from it. So it's as simple as that. That's why if you look at stoi, well, this will be pretty long. You can see, right? This is 20,000. So you have the word and then you have its position in the vocabulary, basically. And this is based on what the counter gave us. Because we can do itos, which is, well, you can already see it's integer to or index to string. Is the opposite, right? You can check this the index in the vocabulary, it'll give you the word that is in that position. I can see that all the words come from the corpus of data that we pull down from IMDb. You can even see the way it's split. Sometimes you even see these funny punctuation marks and all of that. So that is what we have. Now, with that, we can now do encode. So encode is the next step. Tokenize is the first step, right? Then the story and ITOS is to help you easily encode. So when you want to encode, right? Now this encode is combining both tokenization and the actual encoding, the indexing. That's why to encode is going to take the entire string, the entire paragraph, right? It will now tokenize it. This tokenize will now generate a list of the words in this text, right? Then for each of the words in these tokens, which is each a token, each of the words, it will now generate the index position, right? So story.get will get, okay, given this word or this token, what is the index position? Story, remember, is string to index. So it's going to go through the string, as you can see, and get you the index. But if it does not find, that means the word does not exist. So you use unknown. In this case, you are getting the index of the unknown value, which is one. So when you do encode of a text, you effectively end up getting a list of numbers that correspond to the index, right, of that word in the vocabulary, or one if it is an unknown word, right? Then we now create data set. So the data set is going to basically do what we just did here. We did it, you know, one by one. But what the data set now does is that a data set allows you to gather the data that you use to train your model, right? So we create a simple class that will translate the text itself, right, into a list of indexes or indices into the vocabulary. So we are just doing the same thing, right? So when we initialize the data sets, these are the texts. So we are going to first of all establish the sequence length. So here, sequence length is a fixed number. We don't want to train on more than that. Okay. Self data is actual data, which is going to be the encoded text from the data set, from the IMDb text corpus. So we now go through the text, right? So for each text, remember, this text contains the original data that you pulled in from here. Remember, you have a data set, right? This data set, we pull it and we have these ones that we were showing here, right? So it is the number of paragraphs, and they are right now they are 1,000 because we pruned it down to 1,000, right? So this text is essentially a list of 1,000 paragraphs. So for each paragraph in that 1,000 paragraph, you encode it, right? When you encode, what is essentially happening is that, of course, you are converting a paragraph into a stream of words that make up that paragraph, and you're encoding each stream into the index of that word in the vocabulary, right? So what you now have is encoded is now for each word is a list of the indexes of each word in that paragraph in the vocabulary. But remember, text could be a variable length text. So it's variable length. So because it's variable length, you have to pad the remaining one. And that's what this does. So what this basically is doing is that it is checking the length of the encoded, which is the number of words in that sequence, right? And it's subtracting from that the sequence length so that this actually is going to count for the balance. So for example, if the sequence length is 50 and the number of words in this sequence is 20, that means you need to pad 30, um, pads, 30 words basically to make up that 50. If the number of words in the sequence is 40, the sequence length is 50, so the pad has to be 10, right? So I is basically essentially saying for each location in the remaining 10 that hasn't been filled up, right? Fill up the X value with with the pad, right? Fill up the X value with the pad. So the X is the encoded value from I to I plus sequence length, right? While Y is the encoded value I plus 1 to I plus sequence length plus 1. So the other thing that this is also doing is apart from padding, um, what this is also doing is that is picking up the X values and is also generating the Y values. So this is saying these are the X values, which are essentially okay. Well, this is I. So basically, what this is doing is um, I to length of sequence is taking the full it's taking a chunk of what is in the sequence length, and it is then taking the one um that's the X. So let me see if I can explain this with an example, just to explain what is going on here, with a sketch rather. So the idea is this: you have the encoded. The encoded is the text itself that you have encoded, right? Let's assume that each of these boxes represents let's assume that each of these boxes represents a single word in the sequence. Okay, so we have a few words there. So that's what you have here, right? So you can just keep thinking about it that way, that it just goes all the way to the end. Then, so in each of these boxes corresponds to a word, which after encoding corresponds to an actual number, right? And the number is essentially position. So this can be any number, between whatever and so on, right? These are the positions of the words. Now, what X is doing is that we are going essentially saying that the first X, right? We have the flexibility to go the length of uh, the extra length, right? So it's more or less saying we can take this length, right, which is equal to the sequence length, right? X. So we take these first values as the X, right? And let's assume that the sequence length is maybe 50, which is what we have. So what we are saying is that we have a length of 50. So we take the first 50, right? And that is X, okay? Then um then the then for Y, we take the next 50, right? For Y. Okay. Um First 50 for X, the next 50 for Y. That's what's happening here. And right? So the first 50 is put in X for I, and then I plus 1, to I plus sequence length plus 1. So the next 50 is taken for Y. So that's what's happening here. And it just keeps going like that. So you just keep, it's a sliding window basically, right? What that sliding window is doing is that it is taking this first 50, right? Let me use a different color here. So it takes the first 50 sliding window, right? Then that's the X, and then it moves next 50 plus 1, starting from, sorry, the next 50 from the next position, it takes that as a Y. Then when it comes back again, it will now take this next one that was Y before as X, right? And then takes the next one as Y. I think this may have a little challenge with it, but we're going to see how that works. So at the end of the day, you're going to essentially you're creating using a slide window of length equal to the sequence length to pick subsets of this sequence, right? And put it in your X and Y, and that will form the X and Y data, right? That's really what's going on here. So when you now want to get an item, you're essentially getting the data at a particular index. So you're getting a particular window of this data of length equal to the sequence length, right? And then you convert it into a Dodge tensor. So that's what this is doing. Now, let's now create an instance of that by taking the original train text, sequence length. Sequence length, we take it to be 50. We now have a data loader. So create a data loader from this data set. All right. Batch size is 32. So it's always going to take 32 entries. Because what a data set essentially is doing is if you have from every single um, you know, paragraph, right, it's going to generate, use a sliding window like I was showing you before, where you use a sliding window. The only thing is that here in this sliding window, the number of entries in the X is also equal to the number of entries in the Y. So we're not only predicting just a single next letter, we're essentially predicting all of the ones that will come after. So this is more of an encoder decoder kind of thing. Now let me see if I can show you that by taking the first um, piece of the data loader. The loader is just a data loader, right? But we could take, let's see if we can take the first element of the data loader. It's not subscriptable typically, so we can just take the first element of the data set and data set is subscriptable. So when you take this first element of the data set, you see that the X, right, starts from 10, 933, 10, 206, right? But the Y starts from 933. In other words, the Y starts from here. And it's basically going to have exactly the same sequence as the X, except for the first one that's not included. So it starts from 933 and it goes all the way to 136, but then has an extra one at the end. So the sequence of Y is always the same as sequence of X, except that it has one extra at the end, while the X has one extra at the beginning. So that's the sliding window. Okay, so we now have a data set that contains X and Y, right? Where, by the way, you could also do data set one. If you did data set one, let me even just add data set, the next one. You find that the next one, the X will match the Y, the previous Y. You can see here that the X in the second data set, right, basically is the Y in the previous data set. And then, but the Y starts from the next 10, right, and continues, okay, till this 1379, right? But after that, at this point, it now adds the next number. So it's a sliding window, effectively. Okay, so remember when you're doing a transformer, the first thing you always do is a position encoding. You have to do position encoding, right? You do embedding, you do position encoding, then you add the two together, right? Either you add or concatenate. So we have to have a position encoding class, and that's what this one does. So remember, position encoding, we said we could use simple cosine, position encoding, right? Here, this one uses sine, cosine, and I had shown some example of how you could do that in the transformer. We could check the original, um, when we're talking about transformers, right? So when we're talking about transformers, initially, so 12, you will see where it talked about position encoding and the fact that position encoding is what allows you to introduce the sequence information into a transformer. Without position encoding, the inputs would not be able to differentiate um, 2 words or 3 words or 10 words in a particular sequence from what's in another sequence or in a separate sequence, right? So you see that here, the position encoding. And you can see that we talked about the position encoding formula where we use cosine and sine, right? So you have this formula, it's actually very simple. So you see that this is what we used. Basically, we're using a sine for each position I, right? Um, you use the sine, I plus one, you use cosine. So for a word or a word at a particular position, you use the sine for that position, but the next position you use a cosine. And then the position after that, you use the sine again. And the next position you use a cosine. So every even position, you use cosine. Sorry, for every even position, you use sine, and then every odd position, you use cosine. That's what this is doing, basically, skipping between odd and even position. That's why you have a range that goes from 0 to D model and step of 2, right? So for each of the and then this angle is just a calculation based on the position in the sequence, right? So that there won't be um it doesn't grow infinitely, essentially, right? So so that's position encoding. So this is where we are now using it, right? Is that same question? And the way it works is you start off with a value of zeros, right? Max length is the maximum length in the cycle. D model is the depth, essentially the embedding depth, the number of vector, the size of the embedding vector. Essentially, that's what D model is. So you now calculate the position, right? And that position is you take a number in this range from 0 to the max length. So max length is the maximum length you go before you have to start the cycle again. And then on squeeze is to turn it into a two-dimensional number. Then you will now use exponents, you calculate an exponent, right? Which is basically what we just did here, right? And then that exponent multiplied by a negative log of 1000 divided by D model. And that gives you a division, a term that you now multiply by the position. And then you use that one and apply sine to it. So effectively, what is happening is that you create for every even number, this basically does every even number, starting from 0. For every even number, you now calculate the sign based on the position. And then for every odd number, which starts from 1, again, skipping two steps, it will use a cosine. And then you unsqueeze to 0 again. So you will now end up with a vector that represents the position encoding. And then when you take that vector when you want to now do actual position encoding, you will now take that vector and essentially append it at the end of the x values. So this is x plus. You add it to the value of position encoding. Okay, this one is not appending. This is actually sum, right? It is a sum of this um, up to the size of the first dimension, right? So it's a bit. It's. I think it would have been better to have a sketch to give a more intuitive idea of this. But the best way to look at it is to look at what we have here, which is basically saying that you are using some kind of. I think I have a sketch here that explains position encoding much better, so you can just see it and understand intuitively what it is. I'll bring up something that helps with that. So this is what does position encoding. Then we now build the actual transformer language model, right? So you build this by having the two elements that we have already built. We have an embedding layer. So remember we said an embedding layer is a layer that's going to contain the um, the embeddings, right? And the embedding layer, all you need to do is to pass the embedding matrix into it, right? An embedding layer is a layer that will translate the it's going to translate the indexes, which will be the actual input. The actual input into the transformer will be the indexes of each word. But it's going to translate these indexes into a vector whose size is G model. So for you to create an embedding layer, you create an embedding layer with this dimension. Interestingly, in this embedding layer, we created it. We did not use pre-trained embeddings. We could have used Glove or Word2Vec, right? But here, we just created an embedding layer. And we're going to train this model. This model is going to learn its own embeddings. So that's what is happening here. We're not using pre-trained. The last time I showed you that you could use pre-trained, which is what we did with the LSTM. But here we are just using a blank embedding layer that is initialized to random numbers. I only need to give it its dimension, its size, which is a vocabulary size. That's a number of entries in that embedding. And then D model, which is the size of each embedding vector that it should learn. So we have an embedding layer. Then we have a position encoding layer, which is basically this position encoding that we already did here, which I'll try to explain this a bit more with drawings. Right. So we have that. Then now we are using a transformer decoder layer. Interestingly, we're not using an encoder layer, which is why when you're training decoder layer, you actually use two sequences. If it was an encoder layer we're training, the X and Y, the Y has to be a single value or a distribution of values, right? But here, instead, what we did was we generated our Y values to be the next sequence. So essentially what we are having is, as our X value is the sequence, and then the Y value is the sequence that follows immediately, the next entry or the next token, right? Throwing away the token before. So essentially what this is doing is I have this sequence, right? The next from this one next to the next one that comes outside is what we're trying to predict. So that's how you train a decoder model. You typically train a decoder model by giving it two sequences, right? And because it's a decoder model, remember, you have to give it the entire sequence. Don't worry about, okay, am I giving it the future values to train on? That will be handled by the masking layer. Remember, we have a mask attention layer. After we do the attention, we do the masking. Okay, so with that, you can just create a decoder layer. You can see we're using a standard transformer decoder layer, which comes with touch, right? And then we specify the model, the D model, which is the depth, the embedding size, right? And whatever embedding size that is passed in here is what we use. Is that same embedding size that we use to determine the embedding? size here, and the position encoding, because the position encoding has to have the same um, size as the embedding. Because here, the way we have implemented a position encoding is addition, right? Not concatenation. So we're going to take the actual X value, and we're going to add to the X values the calculated value of the position embedding that matches that X, right? And then of course we are going to transfer this into the device. Should have actually done this before, but I guess the position encoding does transfer to the device where X is. Okay, so that's the decoder layer. Then in the decoder layer, just like a decoder layer, you can specify the number of heads, right? The number of it's multi-head attention, so the number of attention heads, right? Again, this is passing here as a default, so we can go with 4. And then the number of layers, number of transformer layers I want to have, right? So after creating a single decoder layer, we'll now create the entire decoder stack and specify the number of layers I want. And we'll provide an instance of decoder layer that we have configured. So decoder layer is always decoder stack rather is always decoder layer times whatever number you want to put. That gives you the entire transformer, right? But this transformer is a decoder only, it's not an encoder. Then at the end, we also are going to have a fully connected layer, just a single fully connected layer, right? And then this part does the masking, right? So because we need to mask, so we can generate a mask to mask the sequence that we want to pass into the decoder, right? You can see that the mask is generated using the touch.tree, the triangular upper matrix, right? So it's going to take the ones, right? But it's going to do a triangular upper matrix of the ones. That means the upper side of the matrix will be converted to zeros, right? While the lower side will be ones. And this diagonal specifies which diagonal. When you specify diagonal equals to 1, it's typically the main major diagonal, of that matrix. That gives you the mask. So we now fill this mask with values, right? So what this means is that anything that is on the upper side of the mask will have a negative infinite value, right? If the mask is equal to 1, it will have a negative infinite value. So this is a way of creating the triangular upper mask. Let me see if I can explain this again. So let's assume this is a matrix, and then you have the triangular upper this way. So this is a uh, triangular upper. Now this mask is basically pointing to this part of it. Let me, fortunately I don't actually have, but I can color it. So let me color it. This section is a triangular upper. Right? So this mask, the mask is you are creating a mask where this side can be, the values here can be changed. That's what this first section does. Then this second section will now replace every value up here with minus infinity, right? So what you will have effectively is you will have a mask. When you apply the second part, right, where we add, you feel anywhere where the mask value equals to 1. In other words, this upper side, you fill it with minus infinity. So that means that this mask side will have values of minus infinity, minus infinity. Every single cell, right, will be given minus infinity. So the question is, what does this do? The thing with the minus infinity is that when you now do softmax on this, the values are minus infinity because softmax will normalize everything. By the way, here is still ones. The values here are still ones because this was touch ones, right? So the values here will still be 1 for every cell in this lower side. So, but when you now do softmax, what will happen is that when you do softmax, right, um, this part of it that is minus infinity will now have values of zeros effectively. Because when softmax, the lowest values, the lowest numbers always have values of zeros. And minus infinity is the lowest number you can ever get. While these ones that are ones will eventually be, they will be um, essentially normalized. So they will not be ones again, but they'll be decimal numbers that all of them add up to one. Remember, what softmax does is everything that is on this side will add up to one. So, but this mask is just to allow you to remove the upper values or to set all the upper values to minus infinity, while the lower values will be whatever was there, because the mask, you are going to multiply it by whatever is there. So yeah, you end up having this um, upper triangular matrix, like we said, which is what you use to block out future values. So that's generating the mask. So now we bring everything together. So bringing everything together, the forward is you first of all determine the sequence length, which is going to be the size of the whatever the first sample in the X values. Then you generate a mask that has the same size, right, as the sequence length. Okay. Um, and you now take that mask, right, and you do an embedding. So you first of all do the embedding. So this embedding will take X, convert the indexes, which is what X comes in as, converts the indexes to embedding vectors. You now also calculate the position encoding, right? Which will take those embedding vectors, calculate the position encoding, and add it to the embedding vectors. So the output you now have is embeddings that are adjusted based on their position in the sequence. And then you take that embedding and you pass it into a transformer. And since it's a self-attention, we're basically passing the embedding vectors twice. Basically input against itself, then use a mask that will do the upper triangular masking out. Okay, so that's what this output does. Then you take this output, put it through the fully connected layer that is typically at the end of the decoder. That gives you the logic, and that's what this piece does. So effectively, what this is doing is what the decoder is doing. It's doing essentially what we have in the decoder block, right? This mask is what we just calculated. That's what this is. Okay, so again, remember, these are all just functions. We've not started actually running anything. We just defined a class for a transformer based on the position encoding class that we use. Embedding already comes with touch, so we use that. Okay. Now, to now go ahead with this thing. First of all, get the device. So we now get the device. And we can even check the device here. Device is going to be a GPU. So we create a new model, right? A new instance of a transformer model. We move the model into the CUDA device, right? We use Adam, we use cross entropy loss, okay? And that's it. So we now look through the values in the loader. So you see the values in the loader here, right? The X, the Y is always the next in the sequence, okay? So X, Y in loader. So we loaded X, this is the entire X value, right? Which is a list of lists. The Y will start from where we stopped on the X, and there are multiple of them. So you can see this starts from the X starts from 74742686 and ends at 213112. But the Y starts at 2686, which is this second one, 4, and then it will end at 112, and then the next number after 112. Right. So that's the value. Then this is our training loop. We use TQDM to do timing. This is where the GPU comes in. I can see it's running pretty quick. Right. TQDM allows us to have a progress bar. So if you want to use TQDM to see your progress bar, what you typically would just do is import TQDM and then pass into TQDM into the loader, or pass the loader into the TQDM, and it will be as it is counting, as each iteration of the loader is counting it. Okay. So we have 5 epochs. I decided to go with 5 epochs. Remember, we already have 1,000, in our sequence, and from each sequence 1,000 in our data set, 1,000 paragraphs, right? But for each paragraph, I'm generating maybe close to another 10 or so, depending on the sequence length. Okay, so we have a lot of data that we are training, so we don't need too many epochs. So in each epoch, we now do batches. Remember, our batch size was 32. We do multiple batches. and we now run the loop. So just wait for a bit while this loop is running, and then you can see the progress. Hello, can you hear me?
Yeah, I can hear you now. I've not been hearing you
Oh.
since.
I've been speaking all this while. Okay, so where do I start from now? I think we'll have to restart. When did I stop? When did you stop hearing me? When did you stop hearing me? Is it when we were waiting for this to from here, right?
Yes, yes, exactly.
Wow. I've been speaking for the last 20 minutes. Sure. Okay. All right.
I thought maybe it was my network, so I've been trying to log out and log in.
Okay. I think we'll have to edit it from some point. For the last 20 minutes I've been speaking. Okay, anyway, so let me start from here again. I think I'll have to start. Yeah, at this point we have run this word prediction with transformer 5 epochs. So the 5 epochs are complete now, as you can see. And then based on these 5 epochs, we can see what it gives to us. Now, the next thing I want us to do is how do we generate text from um, the trained model? So the first thing is for us to even check what do we even get, right? When we look at what the when we pass some text input, right? So that's where this function comes in, right? So I'm going to first of all create a predict output, right? Because it's not really prediction thinking about it because we're using a decoder now. So it's actually next word generation. Really, that's what it should be. Prediction would have been using an encoder model, and we would only predict a single output. But here, we are generating a sequence which should match what should be the next set of words that will come out using this decoder. So to generate the text, what we have to do is to the model is here, the text comes in. We will now run the we will now run encoding on the text. When you run encoding on the text, you are going to have basically a sequence of indexes, right? Because remember, encoding is 2 steps. The first step is to split the long paragraph into the words that make up that paragraph. And then the second step
Your audio stopped working.
Okay, um so when we have these tokens, which basically contain the list of the indexes, right, or indices of the word in the vocabulary, we pass that as our input to the model. So the model is going to effectively generate an output. Now, I'm just going to print that output straight first. Let us see how it looks like so that we can make some kind of sense of it. We're not going to try to do anything um, fancy, right? We'll just return the logits. So with this now, I'm going to take this function and I'm going to just run it here. So generate text. We pass in the model that we have trained. We ask it to generate the next sequence. So you will see that the model is actually going to generate a sequence. And you can see that the values here, let's see the shape of what we get first of all. So you see the shape is 1, 4, and 20,000, right? 1, 4, and 20,000. So let's make some sense of this. The inputs that we passed in. So let's look at the input that we passed in first. The input has 4. You can see there are 1, 2, 3, 4, right? So the this input contains the first 4 letters. Now it's giving you back 4 letters. Four out. This 4 is the 4 words, right? 4 tokens essentially. It's giving you back another 4 tokens as your output, right? Now this is a batch dimension. So because we only gave you one sample, it's also giving us back one sample. Now this 20,000 is basically, if you go back and check, right? Go back and check, you will see that the vocabulary size is 20,000. If you look at it, the vocabulary size is 20,000. That is, let's see. The vocabulary size is what we had picked before. So vocabulary size is 20,000. So what it is effectively giving us is that it is telling us which of the words among these 20,000 words in the vocabulary, which are the words that are most likely to come out? Which are the words that are most likely to come out? Now, so let's call this, let me just play around with this so that we can understand. Let's call this the logits. Okay. So the logits shape. Okay. So yes, so that's the size. Now let's do something with this. The first thing we want to do is check the last. So this is a sequence, by the way. This is actually a sequence of 4. We can check that whole sequence of 4. If we were to just print the whole thing, right? You see a lot of things that does not really make much sense to us, but you see that you have a sequence of 4. 1, 2, right? 3, and 4. So this 4 represents the 4 tokens or the 4 words that should naturally follow. But these 4 words, each of them has a dimension of 20,000. So this dimension of 20,000 is telling us the one that has the highest value is the one that this model is predicting that is most likely. So you have to find the index of the entry here that has the highest value. It is the index that has the highest value because it is not the actual highest value, right? right? Because you're training it on indexes. So it is the index that has the highest value, right? That is what will give us the actual word. So the question is, which one has the highest value? Which of this? Which of these has the highest value? You can easily find the one that has the highest value by using the max, right? So if we were to do something like np or touch.max, right? We could either use touch.max, right? Let's use touch.max. So if we were to use touch.max and we pass in the logits, and instead of the whole logits, let's just pass in logits at 0, which is the first entry, at the first word, which is 0 also, okay, and this. So this would give us the tensor with the highest value. The max is 25, right? The max is 25. 0 means the 0th word, right? Or the 0th batch, okay? The second 0 means the 0th word. So this is 0, this, right? We now want to find the maximum value. The maximum value is 25. But is the maximum value the word? No. We train this thing based not on the actual word, but based on position, based on indexes. That's how the decoder actually is trained, because what the decoder does is, if you look at this, our last layer in our model had a size. It had an output that matches the vocabulary size. That's it. So the input matches the dimension, which is what's coming from the transformer, but the output matches the vocabulary size. So basically, this is to match the index. I think we did not even train this properly, because we should have turned this into the Y values when we're training. The Y value should have been turned into a one hot, right? Surprisingly, this should have been turned into a one hot, um, which is saying, and I need to check this again, because let's see, the Y values actually represents the number, right? Yeah, the Y values represent the number. So I think there is a small problem in this. Um, yeah, the Y values represent what we are um what we are training on is the Y values are actually the indexes, right? So it's supposed to essentially, we need to convert these indexes to positions. That is what we should have on the output. One way to test this is to take the Y value um, from the first one and do a view. So let's do that. So I think we may have been training this model. That's why the model was actually not very, it wasn't doing well. Let's take the Y values first. Data set 0. This will give us the X and the Y values. Now, data 0, let's see. This gives us just the Y values, right? These Y values contain the index of the next word. So the index of next word should have been treated the same way as the X values, right? Here in the input, the embedding layer converts this to embeddings. So we actually have embeddings coming in at the X input. The transformer gives you output that also correspond to embeddings. The fully connected gives you logics which correspond to what the basically vocabulary size. But not the position in the vocabulary. So yeah, we should be training against one hot. So this should have been one hot encoded. The Y should have been one hot encoded before used for training. I think that is the error here. So let's see how we one hot encode it. That means we have to rerun the training with one hot encoding. So I'm going to correct this and then we'll come back to it, right? Because it means we are effectively we're training against the wrong target, right? Because when you do what I just did here was to take the output that is generated from the logics, and you see that these are essentially positions, right? So if these are positions, then we should have been training with positions as well on the input. That means it should have been one hot encoded. So I'm going to correct for that in the training side of things. But let me show you what I was trying to show. Let's assume it was properly trained. Then what we would have here is if I were to print out all of this, the highest value in X is 25, right? So what that means is that it is predicting that it's predicting a distribution. I could take this. So I think the best way is for me to take this distribution of 2000 and kind of plot it. So let's do a plot so that you can understand what I'm trying to say. The output from the output layer is 20,000 outputs. What that 20,000 output means is that output one means vocabulary, the word at position one in the vocabulary. Output two means the word at position two in the vocabulary. Output zero means the word at position zero in the vocabulary. Output 10 means the word at position 10 in the vocabulary. Output 20,000 means the word at position 20,000 in the vocabulary. So if I plot this, right? So let me just plot logit 00, okay, in a single bar chart. Okay, so I need matplotlib for that. Matplotlib by plot. Right. So I now want to just plot a bar chart. So plt dot bar, right? And I'm just only going to plot the first output, okay? And see how this looks like. Now, okay. So X would be the position, okay? Then height. Well, let me just pass in a value. Okay, so we need to extract this first from the CPU. So we need to extract it first. We need to extract the tensor. Okay, then we need to detach the numpy. Okay, let's see what we get. So there are 20,000 entries that we want to plot on the bar chart. This is taking a bit of time. I'm just trying to help with visualization so that we see what it looks like. Okay. I probably didn't plot this properly. Yeah, I don't think I plotted it properly. So we should, let me extract this first so that we know what we are plotting. Let's get the values. So yeah, distribution of first sequence, right? Basically the sequence 1. So this is essentially saying the first word in the sequence, right? This is the first word in the sequence. I can actually print it so that you can see. So the first word in the sequence, these are the numbers that you would say um, um, tell you the probability that each of these words is in a particular position, right, in the database. So typically, I think the best way to plot this, if I were to plot it as, I would have to do something like range. Yeah, so let's do that range. So that will give me the X values, length of sequence 1 and sequence 1. So when we plot this now, we'll see that we are plotting 20,000 values, and then the heights will match this. So this actually should be a histogram, really, not a bar chart, right? It should be a histogram. Histogram is better for this. Yes. So that's it. But what this is telling us is that most of the numbers are negative, right? But a few are positive. This is the highest value. So the question is, what is the position of this value, right? Is it a position 5 or is it a position 10 or position 20, right? That position that has the highest value corresponds to the word. The word at this position in the vocabulary is most likely the word that should be next. That's what I'm trying to kind of show. So how do we get that? We use arg max rather than getting max. If we were to do max of sequence 1, right, that's just going to give us a maximum value, which is 25. But if we do argmax of sequence 1, it's going to give you the position of the value of the one that has the highest value. Unfortunately, there isn't argmax in standard Python, but there is argmax in NumPy, and there's argmax in PyTorch, right? So, but let's use NumPy in this case. We have to import NumPy, of course. So, okay, so let's see if this works. Right. So you can see here that the highest value is 25, right? But the position in this sequence of this highest value, yes, the highest value is 25. Even though I don't know why I'm seeing less than 10 here. But the highest value here, it says is 25. But the position of that highest value is position 19. So it's actually position 19 that matters to us. Position 19 will be saying the word that is at position 19 in the vocabulary. That is the word that we're trying to predict. So to get that word, you now use the index to string, because the index to string is what contains, that will map the index 19 to which word is in that position. And you can see that that word is movie. So ITOS of argmax is the solution, right? This is going to give us, okay, this is a word. This is basically translating the neural network's numeric output into a word. This is what I was trying to demonstrate. But there's a bunch of other errors there, which, so now the issue is this. If I want to get all of the last word, right? So what we did here was logit 00, right? Sequence is logit 00. Okay, let's just take the whole logit and extract it so that we can play around with it. So let's say sequence now, instead of sequence one, the entire sequence is logits dot CPU. We'll move it to the CPU. We detach it from the grad, and then we numpy. The reason why we even have to detach it is because I should have done this with no grad. So this is the mistake. So I forgot that with touch no grad. I should have done this with no grad. So I would not need to do the detach. If I do this again, then I don't need to do that detaching because there is no, let's see, we don't need to detach anymore because there's no, we still need to move it to the CPU, right? Still need to move it to the CPU. As a matter of fact, we could have moved it to the CPU before we return the values. Yeah, because we move it to the device when we are generating. So on the way back, we should have moved it back to the CPU so that we don't have to do all of this additional stuff that I did in here. Okay, so logits is that um, um, we don't need CPU anymore. All right, we can still use NumPy to extract the NumPy. That's okay, and that's it. So now we can now do max argmax and ITOS. It gives us the same thing. Now, this time around, we don't need to detach and we don't need CPU because that has been done already. So we now take the sequence. Now, sequence is made up of four words in the sequence. Each word has these 20,000 entries in it, which we can then plot. So, for example, sequence 0 is the first word in the sequence, right? And this gives you distribution for that one. Um, yeah, I think I've missed something. Oh yeah, okay. So yes, so sequence 0 is let's just take the first element since there's only one in the batch. Okay. So sequence 0 is the first word in the sequence. It still has its own 20,000 entries that represent where in the vocabulary is that word. Then sequence 1 also is going to have its own 20,000, which also represents where in the vocabulary is that sequence 1, right? And so on and so forth. So if we were to just do max of each of them, right? We could do max of 0, which is the value of the max. But we could also do, let me use numpy's max. Okay, so we could do numpy.max. And then we could also do numpy.argmax. And so this is the first word in the sequence. Sequence is just 4 words. We can do for the second word in the sequence. Okay. So the second word in the sequence, you see it has a slightly different high value, but the position is also different at position 7. And then we have the third word in the sequence as well. So we can just, there are 4 words in the sequence. The third word in the sequence will be sick2. And the fourth word is sick3. Okay, so we have four words and we have predicted argmax, basically the position where those words are. We can then translate these positions into actual words. And the way to do that, I can just do all four of them, is to use the um, index to string, right? And so we can do that. So effectively, let's just make it into a tuple and say the tuple is going to be np.argmax of sequence um, S I or S, let's just say S, right? S for S in sequence. Okay, that will give you four words. Okay, so this is a generator. Let's just make it a list. It doesn't matter. So let's use a list comprehension. Okay, so this gives us the position in the so let's now do the lookup ITOS, and this will now give us the actual words, right? Like we've done before. So we now get movie is not is. So this is how we decode it, right? I just wanted to show you this. So the output is a distribution. You take the argmax, which corresponds to which position has the highest probability, which word in the index based on the position has the highest probability, right? And then you use that argmax to get the index. Then you take that index and you look up the index in the ITOS and you get back the word from it. So that's how you translate the output from the neural network back into the actual words in that sequence. So that's just what I wanted to show. Um, so ideally, right, the prediction from the output should kind of match the input. We had an input here when we're training. This movie is not, right? This movie is not. Now, our decoder has ended up predicting this is predicting movie is not is. So it has effectively predicted the next word, which is. And this next word, right, corresponds to the last in the output sequence. So to get the last in the output sequence, you don't need to get all of the words in the output sequence. To get the last, you use -1. So going back to original logic, right, the original logics, this is how you now get that. This means everything in the batch. -1 means the last in the sequence. And this means everything in all of the 20,000. This is going to give you just the last in the sequence, right? Which is this. You will still need to extract the numpy. Now there is something they call squeeze. So squeeze means essentially convert this into a single dimension. And you can see when you squeeze, all of the extra dimensions are removed. Let me show you the difference between something you squeeze and you don't squeeze. This is the size of something I don't squeeze. Sorry, not size, shape. So the shape of something you don't squeeze, you see it has 1 by 2000, right? One being the one output that the last in the sequence and 2000. But when you squeeze it, this one here will be removed. So it basically just becomes a single dimension of 2000. So that's the benefit of squeezing. So when I squeeze this, right, I can then do the argmax on the squeezed value. In fact, I can just use touch. Touch has argmax as well. It's not just numpy. So if I do that, it gives me 7, which matches the value I had before of item 3, 7. So you now have a value of 7, which maps to the index of the last one. I can now use ITOS to essentially retrieve the word that corresponds to that, right? Yeah, because this is touch, I need to extract the value. So we can use value um, to extract the value from that. Okay, value doesn't work. So we can get numpy and get the numpy value from it. Oh, let's see what the error is. Key error. Yeah, we need to extract the value from the tensor. Um, so I'm missing something. Item. I think it's item. It's item. Okay. So item gives you the actual value. It pulls the actual value out of the tensor, right? Let me just prove that again to show you. If I did it without item, item will still give you, squeeze will give you a tensor. Tensor cannot be used as an index in this array. So item will now retrieve the actual value, which is the number 7. So you can see that is, which is that. So when we put all of this together, that is what we are getting from this, right? So we're effectively doing next token, right? Is touch argmax logits. This is what I just did, which is to say, take only the last item, right? Then this dimension of -1 means take the last dimension, right? And because I don't want to generate the full sequence, ideally, you should be able to generate the full sequence, but this decoder is only giving us the sequence plus what it thinks is the next letter. Okay. So for you to do the full next token, you now have to loop around it, right? So that's something we will do when we come in next week, right? We'll now look at the full generation pipeline. Okay. So I'm going to put all of this together. Yes, this has actually trained and it is giving us a model that predicts, but the prediction is not very nice. I think there's an error. I need to verify that this Y value should have been one hot encoded, right? We should have one hot encoded it instead of what we did here. What we did here was wrong. We essentially squeezed it into 2 dimensions instead of one hot encoding it, right? So it's not actually training on the correct value. Unfortunately, I don't have the time to correct this here, right, in this call, but I'll do that later. But yes, this is how you extract. Now, if I wanted to do generating the text, the interesting thing is that I can now do a loop, right, where I take this output. Remember, this is generating just the next word, but we can take that next word and then pass it back in as the next token, and that's what this is doing. So let me rewrite this as 2 different functions. The first function is to generate the next word, and the next function is to generate the full text. So this is a generate next word, right? Or more likely to predict next word. We are actually trying to predict the next word. So then, but if here I now use a loop, right? And maybe I say, okay, the max length is a maximum number of words that I want to generate. Then what I could do is I can take the logits that has been predicted, and then I still use that in a loop, right? Something like um, for this. Yes, so we're now looping round. Okay, so in this loop now, I take the first tokens, which we have done here. I pass it in. I take this output. This output, I now extract the last, the next token. I extract this next token. I take this next token and I then attach it at the end and use this again, right? And I loop around. So this will just continuously, essentially what this is doing is, if the words were something like this, right? If remember the words that I'm passing in, the first four words, right? Which was what um, is I think, let me see if I can get that again. So what we had as the input was this movie is not, okay? So we have this movie is not. That is the initial, this movie is not. Now, when you pass it into the decoder is going to predict the next sequence. So what it predicted was movie is not is, because it's predicting the next, and it still has to be the same four tokens. So the this has been thrown away, it's predicting the future. So it predicts this is a new word that is added. Now, what we are doing here is that we can take this one that it has predicted and pass it back in as an input, right? So that's why we don't even need, what we did here was to extract it, argmax, and use that and pass it in again as an input. So that's what we are doing here. Extracting this argmax is extracting the last word. Then touch.cat is taking this last word and appending it at the end of movie is not. We remove the this, right, from the X value. We append this one back to it and we pass it, we pass this next token back into, the input, right? And that forms the tokens that we use. And then we still try to predict the next word with this, and it's going to predict another thing. And so we just continue looping like that until we get to the end, and this will be the final of everything, which we can then return. So this kind of essentially ends up generating a whole sequence, right? It generates the whole sequence. And that's what this does. So that's next token generation, or that's next word generation. So if we now run that with this, right, it will it now generates a 54 sequence word, because we kept appending the new tokens and asking it to generate the next one. It started with 4, max length is 50, that's why we have 54. We can then take this 54 and we can run through all of them using this other logic that we had here. Let me bring that one to the top. This, we can basically run this, and that will generate the corresponding sentences that matches it. So yeah, let me show you how you can do that. So basically, in logits, right? But the logits 0.numpy. So we effectively extract, and then for each word in this sequence, we will get we'll basically just get the highest value and look it up. And you can see it gives us this sequence. Then we can join it. So we can do something like dot space dot join, and we'll get back a full sentence effectively. But yeah, this is not this is giving us nonsensical stuff because of what I just said about the fact that we did not properly encode the Y, right? We should have encoded the Y as a one hot. We should have encoded the Y as a 1 hot when we were doing the loss, right? We didn't do a 1 hot. We just took Y, we did view -1, and that's not correct. So we have to encode this as 1 hot. But that will take it a long time to retrain. So I'll show you an updated version of it. So that's how you essentially can use a decoder, train a model, and it will generate output. So this is kind of what we do with the large language models. So when we come in next time, because we've essentially exceeded our time, we will look at pre-training, which is what I was actually doing. You know, we'll look at retraining using transformers, auto model for causal LM, and we use PEFT as pre-training. We will use a fine tuning. We use a pre-trained model, and we'll still use the same IMDb data set, and we'll see how much better performance we'll get, right, from using a pre-trained model versus using our own um, using a fine-tuned model that's been pre-trained versus using our own model and training it from scratch. So we'll do a bit of hands-on on that. So that's it. Are there any questions?